We will continue our discussion with spectral analysis of networks. In the last lecture, we saw that how different linear algebra properties or techniques help you in spectral analysis of the matrices. I mean, finding out the eigenvalues and eigenvectors of the matrices, and these eigenvalues and eigenvectors in terms have several properties, and these properties relate them, some of them to the trace of the matrix, some to whether the matrix is symmetric or not, if there are linear dependence among the rows of a matrix and so on. So, there is you just saw a bunch of theorems which will kind of help you out while analyzing the spectrum of real graphs when you look at the spectrum of real graphs. So, today we will do that. We will start from what is called a rank of a matrix. So, a rank of a matrix, if I think you all have heard of it, is actually the number of linearly independent rows in a matrix. So, a matrix has several rows, and we already saw that you can solve a system of linear equations if all these rows are linearly independent. If they are not, then it's not a solvable system, the matrix is not invertible. So, the rank of a matrix, if it is the number of linearly independent rows, and if we have a matrix which is n by n, then what should be the rank of that matrix for that matrix to be invertible? Is the question clear? So, if A is a n cross n matrix, what should be its rank so that it is invertible? Right. So, if its rank is n, it means all the rows are linearly independent. Also, as we saw, if the rank, if two rows are linearly dependent, then there will be a 0 eigenvalue. So, naturally, the rank of the matrix is number of non-zero eigenvalues. So, for every linearly dependent row, you will get a 0 eigenvalue. So, the biggest subset of rows which are linearly independent is the number of non-zero eigenvalues in the spectrum of that matrix. Now, you can also talk of the algebraic versus the numerical rank of a matrix. What does it mean? So, you can compute exactly what are the eigenvalues and eigenvectors of a matrix. However, that computation is too hard for large matrices, and you often resort to some numerical methods like the powering method. And in such cases, actually what you end up with are not exact numbers like 0, you might end up with a number, say the rank, one eigenvalue of the matrix is 0.001 or something which is very close to 0. So, that is called numerical. So, if you consider something which is close to 0, it is up to you how do you define close to 0. If you consider something which is close to 0 as 0, then what you get instead of the exact rank of the matrix, you get the numerical rank. What it would mean is a row might not be exactly expressible in terms of the other rows, but you can at least approximately very closely express. So, what does it mean for networks? What would a linearly dependent set of rows in a network, the adjacency matrix of a network mean? Suppose A is an adjacency matrix, and we have here one node I, one node j, and so this is what would it mean if they are linearly dependent. Means one example, there are other ways of making them linearly dependent. This is one way of making these two nodes linearly dependent. So, what would this mean? So, what it means is there are two nodes in the graph, one is I and one is j, and all their neighbors are same, right. So, you can replace I by j in the graph, and the graph still remains exactly the same. So, such nodes are called structurally similar nodes, nodes whose all their neighbors are same. Now, it might not be a case, structural similar need not be a 0-1 concept, a binary concept. You can talk of extent of structural similarity. Suppose I and j has each 1000 neighbors. 999 of them are same and only one is different. In that case, what would happen is your one of the eigenvalues will be very close to 0 and not exactly 0. So, that will give you that was what I was talking about, the numerical rank. So, actually the approximately one of the eigenvalue will be very close to 0. So, there is this close relationship between the real rank of a matrix and how many nodes are there which are structurally similar. Sometimes the structurally similar patterns are also called motifs. Motifs are very popular term in especially biological networks, because it is found that certain kind of structures kind of repeat in the network. So, it is called motif duplication, and whenever there is a motif duplication, the eigenvalue 0 repeats itself. So, it need not be just one node, a motif can be a subgraph and it might repeat, and even that will kind of enforce the repetition of an eigenvalue 0. So, now if you have a large graph with a large number of 0 eigenvalues, what can you say about this graph? So, think of it in this way. Suppose you have the spectrum of a graph, this is 0, this is some large number lambda 1 and this is some negative number, and the spectrum looks like this. What it means is the 0 and near 0 values have very high multiplicity. So, what would it mean in terms of the physical structure topology of the network?
Large group nodes are structurally similar. Yeah, so they share the same neighbor, so it's more or less like a clique.
It need not be like a clique, right? So, we saw for clique it is like -1, it repeats at -1 and not exactly at 0. Okay, think of a matrix where we have say n nodes and all are disconnected. Only very few are connected. Even in such a network, the 0 eigenvalue will repeat itself, right, large number of times. So, it need not be also high density. What it means is there are certain prototypical structures, subgraphs of the network, and the whole network is constructed by duplicating these structures. So, I can show you just one simple example. Suppose this is a subgraph and I just make a graph where I duplicate this and I can just continue doing this and so on, and I can build. So, this network looks very regular, and there are certain kinds of patterns which repeat again and again, and in this such a network there will be a high multiplicity of the 0 eigenvalue, or the rank of the adjacency matrix will be very low. So, this is one very important fact which you can study from the the spectrum of the graph. There is another very important thing which is used in the context of rank. It's or context of the study of the spectrum. It's called dimension reduction. Of course, it comes from a different field of study. It's very commonly used in machine learning and other areas, but you can also think of an analogical notion in complex networks. So, what we mean by dimension reduction is a matrix or the corresponding graph is an n dimensional entity. It has n nodes and their interaction, or the matrix has n vectors. It's, as we said, it has n column vectors, or it represents n planes. Whatever way you look at, it's a combination of n entities. But can we represent these n independent entities by a smaller set of more basic entities and their combinations? If this is possible, then we say that actually this whole matrix or the graph is not n dimensional entity, its real dimension is r, which is less than n. So, what is this r? R is the rank of the matrix. So, its real dimension is much less than its actual dimension. Suppose a matrix has 1000 rows, out of which 500 are linearly independent and other 500 can be expressed by linear combinations of this 500. So, you just say these 500 rows are important, and for other rows I will just note down what is the particular linear combination that gives rise to this. So it kind of reduces the dimensionality of this whole structure. Same for networks. So for a clique or bipartite network or complete bipartite network, what you can say is I will have this basic structure and I repeat it n times and I am done. So in such case the graph is regular, or it's by the way, there is a different formal definition also of regular graphs. I am just using the term regular loosely. The graph has a structure which repeats itself. The matrix has rows which are kind of linear combinations. So all these are equivalent. Just try to keep in your mind that all these ideas are equivalent. However, when we talk of dimensionality reduction, we are not talking of a small rank in the sense that, you know, non-zero elements, non-zero eigenvalues or non-zero, the rows which are really linearly independent are x, say n minus r, r, and n minus r are linearly dependent. This is the, you know, very strict definition. Suppose a graph is such that its first eigenvalue is very high, say 1000, the second eigenvalue is say 500, and the next eigenvalue is 10, and all rest are around 0. Even then it makes sense to say that this graph has really only strong 2 dimensions, rest of the dimensions are not that important. So this way also you can do the dimension reduction. So rest of the rows can be approximately expressed as a linear combination of only these 2 dimensions. So this is broadly the concept of dimension reduction, and by that you can represent the graphs or matrices in a more succinct way, a brief way, and this has several names, like people call it multidimensional scaling in machine learning, sometimes it is called factor analysis. So each of these dimensions, what are these dimensions? Okay. So I said the biggest eigenvalue is, assume that is 1000, the next one is 500, and rest are 10 and less than 10, say between 10 and minus 10. So they are very small and close to 0, and we are thinking that we can ignore them. So this eigenvalue which is 1000, the corresponding eigenvector, which is the principal eigenvector, will give you the first dimension or the first factor. It is the vector in which is kind of one of the dimensions. The other one, the 500, will give the other dimension, and everything actually lies in this plane which is spanned by these 2 vectors. You can visualize geometrically in this way. So these are also factors, and what factors are important for what kind of graphs and how the factors should be really interpreted depends on the real network you are looking at. All this will be much clearer when we take some case studies, you know, look at real examples.
So these 2 dimensions are when you project the n-dimensional matrix onto this plane?
No. So what happens is, say every column of the matrix can be visualized as a vector, as we discussed, right? So if A is a matrix, then it can be represented as these columns. Okay. Now suppose you plot these columns on a n-dimensional plane, means plot these vectors. So basically I am just showing you a 2-dimensional example. So this is the 2-dimensional plane, and you have vectors like v1 and v2. So v1 is here, v2 is here, v3 is here. You have several such vectors. However, all of them actually lie on this one single line. So actually this line alone might tell you that all these points are, you know, kind of, it captures all these points. But this is not a very good example, because I don't know how to show it in 3 dimension. It's best to actually visualize this in 3 dimension. So v1, v2, v3 all will make a subspace basically, and this subspace might have smaller dimension, because suppose v1 and v2 are in the same direction, and say v3 and v4 are in the same direction, then only if I have these 2 directions and I say everything are aligned to these 2 directions, and that is all.
See, if we have everything lies on this line, so any line parallel to it is also the
yeah, right. Actually the problem is, you know, in 2 dimensions you can't talk of 4 vectors, because in 2 dimensions more than 2 will be always linearly dependent. So that's why I said 2 dimension is not a good example. If you talk of 3 vectors in 3 dimension, then it makes sense, and they might be orthogonal. So these 3 vectors, x axis, y axis and z axis, they are definitely orthogonal, and you cannot really do anything better. You can't reduce the dimension of them. But suppose you had 3 vectors, but all of them are like this. They all lie in this plane, right? In this case, it suffices to specify this vector and say this is a linear combination of these two. So this is the dimension. So everything lies on this plane.
Going back to the point when you stated that we take the principal eigenvector and the next eigenvector, and then what about the other eigenvectors? Can we express them as some combination of these 2 vectors? Then how do these 2 vectors characterize the other vectors?
These 2 eigenvectors characterize the other vectors. Yeah. So what happens is these 2 eigenvectors are the direction. Yeah, in a sense, yes. So the other vectors you can write as a combination of these 2 vectors. So approximately, not exactly. So the eigenvectors might be, one is like both will lie on this plane and orthogonal to each other. Say maybe x is 1 and y is 1 eigenvector, and then all these 3 other vectors can be written as a combination of these 2. Right? In this particular example, all these 3 vectors can be written as a combination of this x and y.
And if I pick up the first 3,
then you can approximate it better. As I said, it's approximation, so they will be slightly away from the plane. It's not exactly lying on the plane, slightly deviating from the plane. So that's why if all others are 0, then you could have done it exactly, but all others are not 0, so you can only do it approximately. So we already have seen the principal eigenvector, that it's very important. We have seen how rank is important. Now we are looking at the first eigenvector. We have already seen that it's important. We calculate the popularity using this, which we also call the page rank. They are very not exactly same, but related. Now the principal eigenvector is all positive. That's by the Perron-Frobenius theorem. So all entries on the principal eigenvector component, all the entries are positive, or all are negative, means essentially all of them are of the same sign. And there is also another interesting property of the principal eigenvector. It is the direction in which the mean of the projection of the row vectors is maximum. So now we were talking of the column vectors. Suppose you look at the row vectors, then the principal eigenvector gives you another interesting property. So if these are the row vectors, okay, then this principal eigenvector is, suppose I call it V1, then you do x1 dot V1, then it is the projection of x1 in the direction of V1. So you restrict the size of V1 to 1, make this assumption, otherwise this comparison does not make sense. Then you project the second one and so on. Then do a kind of square of them. Actually this square is also not necessary, sorry, x3 V3 and so on. V1. I am taking the principal eigenvector and taking the projection of each row vector on the principal eigenvector. Okay. Then this is maximum. This particular quantity is maximum for the principal eigenvector. For the other eigenvectors, it is not that high. So this is another property of the principal eigenvector. So essentially, in other words, it's the eigenvector in the direction of which most of the row vectors align themselves to, because then only the projections, if they are orthogonal, they will not be kind of.
Is it the maximum out of all the eigenvectors or maximum out of all the directions?
Maximum out of all the directions. If you take all of them, it's the maximum out of all the directions.
So it's basically trying to measure the correlation
Between the rows.
between the rows.
So, it is the direction of the means in which the correlation between the rows is highest sort of. And if you look at factor analysis, this is the most important factor, but if it whether it is the only important factor or not is dependent on what is the value of the other eigenvalues, right. So, if the second eigenvalue is very close to the first eigenvalue, then actually all the eigenvalues are important, both are important, but if the first is really high than the other ones, then only the it is the most important factor. You can say it is the most important factor and so on. Also, I have been talking very vaguely about this importance, like how big and if it is big, if it is large and all. So, when do you say something is really large? So, there is also a very simple measure for this. So, remember we talked about the Frobenius norm of the adjacency matrix, which is also equal to the sum of the squares of the eigenvalues, right. So, this is equal to sigma ij a ij square. So, this quantity is really important. If you do lambda 1, which is the first eigenvector, square by say lambda I square, then you can see this percentage. If this percentage is really high, then it is called spectral coverage. So, then lambda 1 covers a large amount of the spectrum, and if this is not that large, then it does not cover. So, sometime for some real graphs we can see that this is as high as say 90%, this is as high as 0.9. So, the first eigenvalue itself covers 9.9 of the spectrum, whole spectrum. By here the whole spectrum means the square of the sum of the eigenvalues. So, then it means that the first factor is really very important, and as we say, already have seen, it is like closely correlates to eigenvector centrality. It is what is known as eigenvector centrality. The second eigenvector is also very interesting. Now, the second eigenvector is orthogonal to the principal eigenvector. We have seen that. So, if that is the case, then the second eigenvector, what can you say about the entries of the second eigenvector? Need not be minimum, it will be much less than of course first, but the first eigenvector. But what can you say about the entries? All of them positive, all of them negative, what can you say? So need not be equal, but it is very clear that some of them has to be negative and some of them has to be positive. Both cannot be having the same sign, because if all of them have the same sign, then the dot product can't be 0, because the other one had all of them positive. So, for the dot product to be 0, a part of it has to be positive and a part of it has to be negative. So, then on what basis the graph or the nodes gets marked as positive and negative for the second eigenvector? Neighbors should not have the same sign. Okay. So, actually if you work out with a real graph, what you will find is if the graph has largely two clusters. So, if the graph looks like something like this, that here you have a click sort of thing and here you have click sort of thing, and there are very few edges running between them, then the second eigenvector will put one of this side as, it is arbitrary, right, any side can be called positive and any side can be called negative, because you can change the sign without any problem. So, what it does is, if there is the neighbors, it tries to put actually rather the opposite, it tries to give the same sign to the neighbors. So, one side will get as positive and one side as get as negative, and this gives a very good basis for clustering the network. So, there are many algorithms which exploit this property for clustering. How do we know this? So, one thing is we empirically have seen this, and there are also works which try to theoretically establish certain results about this. I can give you reference. There is one very celebrated paper by Ravi Kannan and Santosh Vempala, which says clustering good, bad and spectral, and there they clearly prove that spectral clustering is one of the best clusterings, best possible clustering algorithms. But like all these are really involved, but now can you see devise a method for clustering using this second eigenvector. So, what you do is you find the second eigenvector of the graph. After that, positive negative may not be always a very good way to separate the graph. You might also take the median of the eigenvector components and put one side of them in one cluster, the other side in another cluster. And now take the subgraph induced by this cluster and that cluster separately. Find the second eigenvector for each of these clusters recursively and do this. So, this way you get a hierarchical clustering, and this is also called a divisive clustering because you are dividing the network. So, there is two types of clustering. One is agglomerative, where you take nodes, you assume that initially all the nodes are in separate clusters and then slowly try to join the nodes and build bigger and bigger clusters. Finally, the whole network is one single cluster. So, it is also hierarchical clustering, but it is agglomerative, and because you join, and here it is divisive. You initially assume the whole network to be a single cluster, then divide it into two, and then each of them further and further. And again there are heuristics, tricks on when to stop, and
the eigenvector.
with the second eigenvector you can directly calculate which part falls in.
But that means that there we are assuming just two clusters.
No, so that is why I said it is a divisive clustering. If there are multiple clusters, say there are 20 clusters, it might cluster the graph into say 5 and 15. So, 5 clusters put together and 15 clusters put together, and you do. So, it is true with all kind of hierarchical clustering, right. The number of clusters is one problem there, because ultimately you end up in each node being a cluster, and then they join, The question is at what point they join, how much is the cost of separating them, and even using spectral clustering there are, as I said, tricks and heuristics to know when to stop further dividing one cluster. So, you need not go to a node level separating each node, you have to stop somewhere. So, there are measures which will tell you when to stop. Yeah, you get right, but you have to do it recursively, not first you take the second eigenvector to get two clusters and then recursively get other clusters. So, if it is like I am just giving one hypothetical example, there are 3 clusters like this. Your spectral clustering might give this cluster first, and then when you divide this you get this, but you have to know that I do not need to cluster it further. Otherwise, if you want to cluster it further, it will also get eventually divided. Now, how do you know it? There are, as I said, tricks and techniques, the domain knowledge will tell you, and sometime you can look at some values. Say I said the eigenvector components one side are positive and one side are negative, but suppose all the eigenvectors are around 0, the components are around 0, that this graph is more or less cliquish, I do not need to cluster it any further. So, this kind of heuristics you can use. We will just see one example, a brief example, but before that I would also just very briefly mention that as we said saw that random walk can give you the principal eigenvector, remember the random surfer model. Similarly, there are random walk based models for clustering which are to some extent related to the second eigenvector. So, here are 2 references. If time permits later or sometime we will take them up, but let me also tell you that there are not much theoretical analysis of any of these algorithms. Like for PageRank or this popularity propagation, we know for sure it is the first eigenvector with eigenvalue 1 and so on, but for these there are not much theoretical results, and you can also see that they are very recent, 2005, 2007. So, these are pretty open, somebody can try to work on the theory of what is really happening in terms of the linear algebra, means the properties of the graph, if you can relate them to the spectral properties. So, now we move on to a case study. So, this is a very recent work actually, which I did myself with Animesh and Ravi Kannan. I am taking this example because I am most familiar with this, and this example is has something to do with what is called consonant inventories, but it is a complicated concept. I do not want to get into linguistics. So, I will tell you using another very simple analogy. Think of a movie actor network. So, that I think will be a simpler analogy for you. So, that is a bipartite network. So, in this partition you have the actors, okay. And so S is an actor, P is an actor, and K is an actor, and this L1, L2, L3, L4 are movies. So, you can think of movie 1, movie 2, movie 3 and movie 4, and these edges are there if this particular person has acted in this particular movie. So, if person S has acted in movie 1 L1, then there is an edge. So, a person can act in various movies and a movie can have more than one actor. This is the basic nature of this bipartite network. Now, tell me what the degree of a movie in this network would mean in this particular network. Number of actors the movie has, and the degree of an actor, very simple. So, the degree of an actor we will also often refer to as the frequency of the actor. The frequency of the actor, like how frequently he has acted in different movies, just remember that. So, we can construct an adjacency matrix for this graph. Usually the adjacency matrix for bipartite graph, as we had seen one example, there will be one set of ones here, one set of ones here, zeros here and zeros here, right, typically. But in this particular case we construct a different slightly different adjacency matrix. We have put the movie names here, movie 1, movie 2 and movie 3, movie 4, and we have put the actors here, and you know we have put 1 if this particular actor has acted in this particular movie. So, it is not exactly an adjacency matrix of this network. Since it is a bipartite network, we could write this network in this fashion, in this way we can write it as a matrix. Now, tell me, so if this is A, what is A transpose? What is the physical significance of A transpose?
Whether two actors have worked together.
Right, and the exact value?
The number of movies in which.
Right. So, did you get this point? A transpose will show you how many movies two actors have acted together. Let me just show you. So, here is a actor 1 and here is a movie 1, movie 2 and so on. So, this is your A, and suppose this is 1 and 0 and so on. And when I do A transpose, here are my actors and here are my movies, and here is 1, 1, 0, 0 and so on. So, if I am looking at the ijth entry of this matrix, so this matrix will be marked on both sides by actors, right. AN, and this particular entry, say for this particular A2 and A1, say this particular entry, you take this row and multiply with this one, right. The second column of this gets multiplied with the first row of this. It's very simple matrix multiplication. So, when you do it, what happens? When do you get a 1? When both of them are 1, right. So, it means they have acted in the same movie, otherwise you get a 0 and you then add them. So, this value will be how many movies they have acted together. And what will be the diagonal elements? No, A transpose, I am asking A has acted. So, which is the, as I said, frequency of the actor. Now, to make it a graph without the diagonal entries, we always enforce that the diagonal should be 0. So, we subtract those entries. So, D is nothing but it is a diagonal matrix. So, D looks like this, everything is 0 except for these, which is like the frequency of A1, the frequency of A2 and so on. So, we subtract it. So, after subtracting you get such a matrix. So, all the diagonal ones become 0 and these values are how many times the actors have acted together. So, this is the this is a unipartite graph, and this graph is called the one mode projection of. So, this is a bipartite graph, it is called a one mode projection of this graph, and in a matrix notation you can get it like A transpose minus D. Similarly, you can have A transpose A minus D dash. So, what will be A transpose A? The elements of A transpose A, how many? Two movies have how many common actors, and you again subtract the number of actors in each of the movies, which is the diagonal element. So, you get these two matrices. So, actually we constructed this network for some language data, but think that we did it for the Bollywood data for easy understanding. So, we have a database from where we got it. Now, we are trying to get the spectrum of this network. Let us see what happens. So, see the spectrum, it is very, in fact very difficult to see. The highest eigenvalue is somewhere here, which is greater than 2200, say it is something like 2300, 2300. On the negative end it is like near minus 300, but most of these eigenvalues, so this is the multiplicity, right, the highest multiplicity you get is for 0. So, we get the highest multiplicity for 0. So, what does this mean? This is for basically A transpose matrix. So, this is this particular matrix, this particular graph. So, it is a co-actor graph. So, two actors and nodes are the actors and an edge represent how many movies they have acted together, right. So, in this network we find that most bulk of these eigenvalues are 0, most of them are 0. What does it mean? Okay. So, what property of the matrix it says? The matrix has a large number of linearly dependent rows. So, what it would mean is if an actor has coacted with ABC, then a large number of actors are there who has only coacted with ABC, right. So, there are, you can also think of group as one of your friends mentioned. So, it's more like there are some prototypical acting patterns. There are some set of actors who go with only some set of actors and some other set of actors who go with some other set of actors. In the context of Bollywood, you can think of, Shah Rukh Khan gets always paired with Kajol. So, Kajol, and say in that movie there will be some villain acted by some particular person. So, this cast is very similar, and all this there will be many actors like Shah Rukh Khan and few more, say contemporary actors who will act with the same cast, but there will be another genre of actors, say Amitabh Bachchan and his time, when they will be acting with another set of casts, and that cast will be same. So, Shah Rukh Khan will be representing one sort of motifs and there will be many people who will represent that motif, and Amitabh Bachchan will be representing another sort of motif and many people acting according to that motif. So, there are some prototypical casts, the way movies are made, there are some prototypical casts. By the way, these results are not for the movie actor network, I am just drawing some analogy, this is on some other network, but I do not expect something very different also. So, I guess if you do the analysis, you will really get a lot of 0 eigenvalues. So, this is the first result that you get. The second one which people do, actually these ends of the spectrum are really important, usually important, because it shows how the eigenvalue decays. At least for this is lambda 1, somewhere there is lambda 2, somewhere there is lambda 3. So, how it decays is very important, but from this graph you really can't see how it decays. So, what you do is, say this is the positive end of the spectrum, and we plotted this last few eigenvalues, means the highest few eigenvalues. So, this direction I have the eigenvalues and this direction I have the rank of the eigenvalues. So, the highest eigenvalue, this is a log-log plot, double logarithmic plot. So, the highest eigenvalue is somewhere here, so which is less than 5000 but greater than 500, actually it is 2300, around that. the next one is around say 400, and it decreases in this way, and this shows a linear behavior, right. It looks like a line in a log-log plot. So, if something looks like a line in a log-log plot, then actually it is a power law. So, we found also the exponent, basically the slope of this. So, it shows it is minus 1.33. So, it is important because what it shows is the first factor is really very important. The next one drastically drops, the next one even gets much smaller and it drops faster, but after that the bulk is now at 0. So, there are very few factors which controls this movie actor network. In fact, if you look at the spectral coverage, I talked about the spectral coverage just some time back. 89% of the spectrum is explained by only the first eigenvector, value. Read all of them as values. So, the first eigenvalue covers 89% of the spectrum. The second one is the first and second together covers 92%, the first, second, third covers 93%. So, see this third one actually covers only 1%. So, it means the fourth one will cover even less and the other ones will cover even. So, we do not go further. So, we just stop here, and now we ask the question how the eigenvectors look like. So, this is the first eigenvector plot. This is the first eigenvector component we are plotting, and on this axis we are plotting the frequency. Remember, the frequency of an actor is how many movies he or she has acted in. That is what I am calling here frequency, and the eigenvector component. And we are surprised to see that the frequency has an exact correlation, very high 0.99 correlation with the first eigenvector component. Now, the first eigenvector component, you find the first eigenvector which corresponds to the first eigenvalue. So, that will assign a component to every node, right. Basically, it is a vector, so it will have a value corresponding to ith entry. That value is actually the component on the ith node. That is what we mean by when we say the component. These are the eigenvector centralities. So, basically, the first eigenvector is the eigenvector centrality. So, we have plotted the eigenvector centrality versus the frequency of the actor, and it shows a perfect correlation. No, frequency is the number of movies an actor has acted in, right. That is the definition of frequency, and we saw a very high correlation.
Which actor have you taken?
All the actors, all actors. So, each point corresponds to each actor. So, this is a point corresponding to one actor who has the highest eigenvector centrality. So, the most popular actor in the network. So, who do you think, means what kind of actors they are? Somebody like Amitabh Bachchan? Shah Rukh Khan? Not exactly. They are usually the comedians, or means people who are not in the main roles, but they come in almost all the movies. You can see them in almost all the movies. So, they are actually the most popular according to your first eigenvector centrality. Okay. But the question is it a trivial result, or does it say something interesting about the graph?
They show that the degree of which node here is highly correlated to the eigenvalue component.
Yeah, that is what they show. But what I am asking is it, so does it speak, will it happen in every graph, or is it some special property of this graph, some special property of this particular system that's giving rise to such property? Actually, what it is telling us is about, it's called proportionate co-occurrence. I will write the term first. I will explain this later, but I will take one extreme case first. Think of a matrix where this is a coactor matrix. Sorry, I did a small mistake. I will draw another one. Think of a coactor matrix like this. Here, actor 1 has acted with actor 2, m1 times, right, and actor 2 has, it's a symmetric matrix, acted with actor 2 with m1 times, but they have not acted with anybody else. The same is true with actor 3 and 4 and actor. So how the graph looks like? Right, the graph will look like a set of edges. It's just a collection of edges with weights m1, m2 and m3. And suppose m1 is greater than m2 is greater than m3. Okay. Now I ask you, what's the first eigenvector, the largest eigenvector of this matrix, and what is the largest eigenvalue of this matrix? Think of this vector, the first two are 1 and all of them are 0, right. So then it will yield this vector m1 m1, right. Can you see this, that this is an eigenvector? If you multiply this by this vector, so this, let me call it x. So this vector, the first one will be m1, the second one will be m1, and the rest of them will be 0. So this is the eigenvector, and it has the eigenvalue m1. And since m1 is greater than m2 and greater than m3 and so on, m1 is the largest eigenvalue, because the other one will be m2, and m2 will also have 0 0 1 1 as the eigenvector and so on. So m1 is the largest eigenvalue, and the corresponding eigenvector is 1 1 and all zeros. And what are the frequencies? So frequencies is the first actor acts in m1 movies, isn't it? He has only acted with one person and acted on m1 movies, so his frequency is m1. The second person is also m1, the third one is m2 and so on. So is there a good correlation between these two vectors? Is there? If you plot, what happens? So what happens is, there will be two actors on m1 who has 1 and rest all will lie on 0. So it won't look like a nice line like this. It will be rather an inverse correlation. Yeah, sorry. Yeah, so 1 will be here and the rest will be here. Yeah. So there will be no good, this is m1, this is m2, this is m3. So there will be no good correlation, because most of them are here and you don't see this nice line like as you were seeing here. So this doesn't happen for every matrix. On the other hand, since we don't have much time, I leave the proof for you, but if you think in this way, that suppose the first person, I take the actors, right, actor 1, actor 2 and up to actor n, and I say this person acted in f1 movies. So these are the frequencies, and I define this matrix as this, as follows. So these are all zeros. This is f1 f2, f1 f2 by some normalization factor. So what it means is, I have acted in f1 movies and you have acted in f2 movies. By random chance, actually we act in f1 f2 by some normalization constant, right. That's if we randomly choose movies while acting. If this is the matrix, you can very easily show that the first eigenvector is actually f1 f2 f3 and fn, exactly the same one. Actually for that you have to have f1 square here. So you don't need to, if you subtract the diagonal entries, there will be slight changes, but that's why the correlation is not 1 and 0.99. So this is what is called proportionate co-occurrence. So two actors co-act proportionately, in proportion to what? The number of movies they have really acted in. So in such kind of networks, you see such type of a property, that the first eigenvector will exactly correlate with the frequency. So this is like another insight that you can gain from the eigenvector and the correlation between frequency from graph, for a graph. What about the second eigenvector? So now we have plotted the second eigenvector components here and frequencies here, but you can also think of the first eigenvector components here, because first eigenvector components and frequencies are the same. So what's happening in this graph? You can see clearly that there are two limbs, as you would have expected for the second eigenvector. So there are some parts which are getting the negative components, some part which are getting the positive components, and lot of them are around 0. See, interestingly, things which are the actors who have very high frequency, that is very popular actors, are neither on the positive side or on the negative side. What it means is they are part of both the clusters actually, and people who have acted in very few movies, their frequency is really low, are also not split properly. This is because there is very little evidence to split them actually. They don't connect to, they hardly connect to any people in the whole network. They are like dangling nodes scattered here and there. But rest of the nodes which are like in the middle frequency zone, well behaved, they get nicely clustered into two, paths. And these paths might be like in the movie actor network, you can just try to guess, I don't know, because this is for a different context, and for this we had a very nice explanation, for linguistic explanation of why this split happened. But for individual graphs, means for different graphs, the explanation would be different. So you have to really look at the nodes and how the split happened and so. But it clearly shows like how it really clusters the graph. It splits the graph into two parts. So this is what I had to say about the spectral analysis of graph. At the end, I would just mention one thing, that this whole field of spectral graph theory, or at least spectral analysis of complex networks, is really very new. Not much work has been done. There has been some work in isolation here and there. There is no comprehensive theory, but it seems that there is a lot of scope here. It's a rich area, and although in traditional graph theory there has been a lot of work, spectral theory in general there has been a lot of work, but it has rarely been applied to real world graphs and to study their properties. One problem is because these graphs are large, and to get their whole spectrum is really difficult. But now we do have very fast computers and methods to algorithms to do that. So this is a very rich research area, and I encourage all of you to go and look for other kind of works in this area.